Subscribe to the channel so you don't miss out on any of these videos. Imagine a colossal stream of energy, so powerful it could stretch across millions of light years, shaping the very structure of the universe itself. These streams, known as black hole jets, are among the most mysterious and awe-inspiring phenomena in space. But what if I told you that these jets aren't just random bursts of energy? What if they're nature's most extreme particle accelerators, capable of pushing matter to near light speeds and affecting galaxies billions of years after their formation? How does a black hole, the very definition of darkness, create such brilliant and destructive displays? By the end of this, you'll understand not only what these jets are but also the profound ripple effects they have on the universe, and why scientists are still struggling to explain their true nature. Black hole jets are, quite literally, cosmic fireworks on a scale that's hard to comprehend. To start, we need to unravel the basics of what they are. Imagine a supermassive black hole, a gravitational monster millions or even billions of times the mass of the Sun. These black holes sit at the center of most galaxies, quietly, or sometimes not so quietly, devouring anything that ventures too close. Gas, dust, and even entire stars can fall victim to their immense gravitational pull. But instead of vanishing without a trace, some of this material doesn't actually fall into the black hole. Instead, it gets superheated and accelerated, forming a swirling disk of plasma around the black hole, known as an accretion disk. From this disk, black hole jets are born. Here's where it gets fascinating. The process of creating these jets isn't fully understood, but what we do know is that the intense magnetic fields around the black hole play a key role. As matter spirals into the accretion disk, it generates a tangled mess of magnetic fields. These fields are then twisted and stretched by the black hole's rotation, creating an immense buildup of energy. Like pulling back a slingshot, the black hole's magnetic forces eventually release this energy in the form of narrow, focused beams shooting out from its poles, jets that are packed with particles moving at relativistic speeds, which means close to the speed of light. Now, let's talk about what these jets do. First, they can stretch across unimaginable distances. Some jets have been observed extending millions of light years away from their source black hole. To put that in perspective, if our Milky Way galaxy were the size of a frisbee, one of these jets could stretch from Earth to the Moon. But they're not just pretty lights in the cosmos. These jets are essentially massive particle accelerators, far more powerful than anything humans could build on Earth. The Large Hadron Collider, the most powerful particle accelerator we have, pales in comparison. While the LHC can accelerate particles to around 99.999999% of the speed of light, black hole jets do the same thing but on a scale that's trillions of times larger. The energy within these jets isn't just local, it impacts entire galaxies. As the jets blast through space, they slam into surrounding matter, heating it up and creating enormous shockwaves. This process can trigger the birth of new stars by compressing gas clouds or, paradoxically, quench star formation by blowing away the gas needed to form stars. In essence, black hole jets can both create and destroy, acting as cosmic sculptors that shape the evolution of galaxies over billions of years. But here's where things get even weirder. While these jets originate near the black hole, the particles in them never actually cross the event horizon, the point of no return. Instead, the jets are formed outside the black hole, in the region just above its poles, called the relativistic plasma region. This is one of the reasons black hole jets remain such a mystery. How does matter, in the presence of such an overwhelmingly strong gravitational pull, escape being swallowed? And why do the jets take on such precise, focused shapes rather than dispersing in all directions? One theory involves something called the Blandford-Znajec process. Named after the scientists who proposed it, this process suggests that the black hole's rotational energy is tapped into to power the jets. Essentially, the black hole acts like a cosmic dynamo, converting its spin into an electromagnetic force that launches the jets. But even this theory doesn't explain everything. For instance, why do some black holes produce jets while others, seemingly identical, do not? Why do the jets vary so much in brightness and length? These are questions that keep astrophysicists awake at night. Another fascinating aspect of black hole jets is their role in regulating galaxy formation. Galaxies are messy, dynamic systems, and supermassive black holes often act as the central engine driving their evolution. Jets can heat up the intergalactic medium, the thin soup of gas that fills the space between galaxies. By doing so, they prevent this gas from cooling and condensing into new stars. Without this regulation, galaxies could grow uncontrollably, potentially disrupting the balance of the cosmos. In this sense, black hole jets aren't just chaotic explosions, they're also part of a delicate cosmic feedback loop that helps maintain order in the universe. But these jets aren't just interesting from a scientific perspective, they're also deeply philosophical. They challenge our understanding of extremes. Black holes are places where gravity reigns supreme, where the laws of physics as we know them break down. Yet, from these regions of chaos and destruction emerge some of the most organized and powerful structures in the universe. How is it that something so destructive can also create such immense beauty and complexity? The more we study black hole jets, the more questions arise. For instance, what role do they play in the larger context of the universe? Are they mere byproducts of black hole activity, or do they serve some greater purpose we have yet to understand? And what about their relationship with dark matter and dark energy, the mysterious components that make up most of the universe? Could these jets somehow provide clues about the nature of these elusive phenomena? Black hole jets also challenge our perception of time and scale. These jets can last for millions of years, meaning that the events we observe today started long before humans even existed. The light and energy emitted from these jets take thousands or even millions of years to reach us, offering us a window into the past. In a way, observing a black hole jet is like reading a cosmic history book, where each particle of light tells a story about the early universe, galaxy formation, and the extreme conditions near black holes. And then there's the incredible distance over which these jets exert their influence. While their physical structures stretch across millions of light years, their effects ripple out even further. The particles carried in these jets can collide with interstellar material, triggering reactions that send shockwaves through entire regions of space. This process can alter the chemical composition of intergalactic gas, potentially influencing the formation of new stars and planets. It's mind-boggling to think that a single black hole at the center of a galaxy can have an impact on areas of space that lie millions of light years away. One particularly intriguing aspect of black hole jets is their connection to gamma-ray bursts, GRBs. These are some of the most energetic explosions in the universe, capable of outshining entire galaxies for brief moments. Some GRBs are believed to be tied to the formation of black hole jets. When a massive star collapses into a black hole, it can form jets that emit intense bursts of gamma rays. These bursts are so powerful that if one were to occur too close to Earth, it could strip away our planet's atmosphere. Luckily, the chances of such an event happening nearby are extremely slim. Despite their danger, black hole jets and GRBs could also hold the key to understanding the origins of heavy elements like gold and platinum. These elements are thought to be forged in the extreme conditions of these energetic explosions. Without them, the universe, and life as we know it, would look very different. In a way, black hole jets are part of a cosmic alchemy that helps shape the building blocks of the universe. Let's take a closer look at the mechanics of these jets. The particles within them, mostly electrons and protons, are accelerated to nearly the speed of light. As they move, they interact with magnetic fields, spiraling along them and emitting radiation. This process, known as synchrotron radiation, is what makes the jets so bright and visible across vast distances. But the brightness of these jets isn't uniform. Observations show that the central part of the jet is often brighter than the edges. This difference, known as limb brightening, is thought to result from the way particles interact with magnetic fields and the angle at which we observe the jets. Interestingly, the orientation of a jet relative to Earth can drastically affect how we perceive it. When a jet is pointed directly at us, it appears much brighter due to a phenomenon called relativistic beaming. In such cases, the jet is referred to as a blazer, a type of active galactic nucleus that is among the brightest objects in the universe. Blazers are essentially black hole jets turned up to 11, and studying them provides valuable insights into the physics of relativistic jets. But black hole jets don't always behave predictably. Sometimes, they flicker or even shut off entirely, only to reignite later. These changes are thought to be related to fluctuations in the black hole's accretion disk. When the flow of material into the black hole slows down, the jet weakens or disappears. Conversely, when the accretion disk becomes more active, the jet can surge in brightness and power. This variability adds another layer of complexity to an already enigmatic phenomenon. In recent years, scientists have begun using computer simulations to study black hole jets in unprecedented detail. These simulations model the behavior of matter and magnetic fields near black holes, providing a virtual laboratory for testing theories. One of the most exciting developments in this field is the use of machine learning to analyze the vast amounts of data generated by these simulations. By identifying patterns and anomalies, researchers hope to uncover new insights into the mechanisms driving black hole jets. Despite these advances, many questions remain unanswered. For instance, what determines the direction of a jet? Why are some jets tightly collimated while others are more diffuse? And what happens to the particles in a jet once they've traveled far from the black hole? These mysteries remind us that, for all our technological progress, the universe still holds secrets that defy human understanding. As we explore these questions, black hole jets also provide a unique opportunity to study fundamental physics. The extreme conditions near black holes, where gravity, magnetism, and relativistic speeds all come into play, create a natural laboratory for testing theories of particle physics and general relativity. For example, studying the interaction between particles and magnetic fields in black hole jets could help scientists understand how cosmic rays are produced. These high-energy particles constantly bombard Earth, but their origins remain largely unknown. Black hole jets might be the missing piece of the puzzle. Beyond their scientific significance, black hole jets also inspire a sense of wonder and curiosity about our place in the universe. They remind us of the sheer scale and complexity of the cosmos, as well as our limited understanding of it. While we've made incredible strides in observing and studying black holes and their jets, we've only scratched the surface of what there is to learn. The next frontier in this research will likely involve new telescopes and instruments capable of capturing even more detailed observations. Projects like the Event Horizon Telescope, Ejected, which famously captured the first-ever image of a black hole, are already pushing the boundaries of what's possible. By combining data from multiple observatories around the world, the Ejected creates a virtual telescope the size of Earth, enabling unprecedented resolution. As this technology improves, we may soon be able to observe the intricate details of black hole jets and uncover new clues about their nature. The Event Horizon Telescope, Ejected, is just the beginning of a revolution in our ability to study black hole jets. Future observatories, such as the proposed Lynx X-ray Observatory or next-generation radio telescopes like the Square Kilometre Array, SK, will allow us to peer deeper into the hearts of galaxies and track the evolution of jets over time. These instruments will provide higher resolution, broader wavelengths of light, and faster data collection, enabling us to capture fleeting events that were previously undetectable. For instance, one key area of research is understanding the moment a jet forms. Observing a black hole during the early stages of jet formation could provide crucial insights into the processes that launch and sustain these cosmic accelerators. However, catching a black hole in the act of launching a jet is incredibly challenging because these events occur unpredictably. Advanced telescopes equipped with rapid response capabilities could change that, giving astronomers a chance to observe these phenomena in real time. Additionally, the study of black hole jets may intersect with other fields of astrophysics. For example, their influence on galaxy formation ties directly into our understanding of the cosmic web, the large-scale structure of the universe made up of galaxies, gas, and dark matter. Black hole jets play a role in shaping this structure by injecting energy into intergalactic space, preventing the collapse of gas into new galaxies in some regions while triggering star formation in others. The interplay between jets, galaxies, and the cosmic web is an emerging area of research that promises to shed light on how the universe has evolved over billions of years. A fascinating development in recent years is the use of gravitational wave observatories to study black holes. While gravitational waves are primarily associated with the collisions of black holes or neutron stars, they might also provide indirect evidence of jet activity. For instance, if a black hole with an active jet merges with another black hole, the jet could leave an imprint on the gravitational waves produced during the collision. This idea is still theoretical, but it highlights how different branches of astrophysics can come together to deepen our understanding of black holes and their jets. The extreme environments around black hole jets may also offer clues about dark matter and dark energy, two of the biggest mysteries in modern physics. Some theories suggest that interactions between dark matter particles could produce detectable signals in the high-energy environments near black holes. Similarly, the energy distribution within jets might provide indirect evidence of how dark energy influences the universe's expansion. While these ideas remain speculative, they underscore the potential of black hole jets to act as laboratories for exploring some of the most profound questions in science. Another intriguing question is how black hole jets interact with their host galaxies on a more localized scale. For instance, jets often sweep through dense regions of gas and dust within a galaxy, creating shock waves that can compress the material and trigger star formation. At the same time, the energy released by jets can heat up surrounding gas, preventing it from cooling and collapsing into new stars. This dual role makes black hole jets both creators and destroyers, capable of nurturing or stifling the growth of galaxies. The balance between these effects likely depends on a variety of factors, including the size and speed of the jet, the composition of the surrounding gas, and the age of the galaxy. Moreover, black hole jets may influence the chemical makeup of galaxies. The particles accelerated in these jets can interact with interstellar gas, producing elements and compounds that would not otherwise form. This process, known as cosmic ray spallation, can create isotopes that serve as markers for past jet activity. By analyzing these isotopes in the gas and stars of a galaxy, scientists can reconstruct its history and gain insights into the long-term effects of black hole jets. Beyond their scientific importance, black hole jets also capture the imagination of the public. Their sheer scale and power evoke a sense of awe, reminding us of the vast forces at play in the universe. Images of jets stretching across millions of light-years are some of the most striking representations of cosmic phenomena, inspiring curiosity and wonder in people of all ages. They challenge us to think beyond the confines of our everyday experiences and consider the incredible diversity of structures and processes in the cosmos. The role of black hole jets in popular culture is another fascinating aspect. From science fiction stories to documentaries, these jets are often portrayed as symbols of the extreme and the unknown. While some depictions take creative liberties, they reflect our collective fascination with the mysteries of space and our desire to understand phenomena that lie far beyond our reach. This cultural significance makes black hole jets not only a subject of scientific inquiry but also a source of inspiration and storytelling. As we look to the future, the study of black hole jets will likely benefit from advances in artificial intelligence and data analysis. Modern observatories generate enormous amounts of data, far more than any team of humans could analyze manually. Machine learning algorithms are already being used to sift through this data, identifying patterns and anomalies that might otherwise go unnoticed. These tools could help scientists discover new types of jets, identify rare events, or even uncover entirely new phenomena associated with black holes. While we've made significant progress in understanding black hole jets, it's important to remember that our knowledge is still limited. The universe is vast, and black holes are among its most enigmatic objects. Every new discovery raises additional questions, reminding us of the complexity and mystery of the cosmos. Yet, it's this very mystery that drives scientific exploration, pushing us to develop new technologies, ask deeper questions, and expand the boundaries of human knowledge. Black hole jets are more than just cosmic particle accelerators. They are gateways to understanding the universe itself. They connect the smallest scales of particle physics with the largest structures in the cosmos, bridging gaps in our knowledge and offering insights into the fundamental nature of reality. As we continue to study these incredible phenomena, we not only learn about black holes and galaxies but also about the forces that shape the universe and our place within it. The profound mysteries surrounding black hole jets remind us of the interconnectedness of the universe. These extraordinary phenomena, born from some of the most extreme conditions imaginable, offer a unique lens through which to explore fundamental astrophysical principles and the broader dynamics that govern galaxies and cosmic evolution. Despite decades of research, each new observation seems to unveil even more complexities, driving a relentless pursuit of understanding among scientists. One of the most exciting aspects of black hole jets is their ability to challenge and refine existing scientific models. For instance, the exact mechanism that powers these jets is still a topic of intense debate. The prevailing model, based on the Blandford's-Ejected process, relies on the extraction of rotational energy from a black hole's spin through interactions with its magnetic field. However, alternative theories suggest that the energy could also originate from the accretion disk itself, or even a combination of both mechanisms. As new data emerges, scientists are continually testing these theories, often uncovering surprising results that defy expectations. Take, for example, the enigmatic phenomenon of jet stability. Given the immense distances these jets travel, sometimes spanning entire galaxies, one would expect them to dissipate or scatter over time. Yet, many jets remain remarkably coherent, maintaining their narrow structure over millions of light years. This stability is thought to be due to a combination of magnetic fields and relativistic effects, but the precise balance of forces that allows such coherence is not fully understood. Studies using simulations and observations aim to unlock this mystery, potentially shedding light on broader principles of fluid dynamics and magnetism in extreme conditions. Another puzzle lies in the variability of black hole jets. Observations reveal that jets often flicker or pulse, emitting bursts of radiation that can vary in intensity and frequency. These fluctuations could be caused by changes in the black hole's accretion disk, interactions with surrounding material, or instabilities within the jet itself. However, the exact causes of this variability are still under investigation. High-cadence observations, which capture rapid changes in brightness, are helping astronomers piece together the puzzle, revealing connections between jet activity and the dynamic environment near a black hole. The role of black hole jets in cosmic feedback is another area ripe for exploration. Feedback refers to the processes by which black holes influence their surroundings, regulating the growth of galaxies and even affecting the larger-scale structure of the universe. Jets play a central role in this feedback by injecting vast amounts of energy into the intergalactic medium, preventing gas from cooling and forming new stars. Yet, the efficiency of this process and its long-term effects remain poorly understood. Researchers are using sophisticated computer models to simulate these interactions, hoping to uncover how jets shape galaxies over billions of years. Additionally, black hole jets may hold the key to understanding the origins of the most energetic particles in the universe, cosmic rays. These particles, which travel at nearly the speed of light, are thought to be accelerated by shock waves within jets or by interactions with magnetic fields near black holes. By studying the composition and energy distribution of cosmic rays, scientists can gain insights into the processes occurring within jets and the environments they traverse. This research could also have practical implications, as cosmic rays can affect space travel and even technology on Earth. One particularly intriguing question is whether black hole jets could provide clues about the nature of dark matter. Some theories suggest that jets might interact with dark matter particles, producing detectable signals such as gamma rays or other high-energy radiation. For example, if dark matter consists of particles that can annihilate or decay, the energetic environment near black holes could amplify these processes, making them observable from Earth. While these ideas are speculative, they highlight the potential of jets as natural laboratories for probing fundamental physics. Black hole jets are also helping astronomers map the distant universe. Their intense brightness and narrow beams make them excellent lighthouses, allowing scientists to study the intervening material between the jets and Earth. By analyzing how the radiation from jets is absorbed or scattered by gas and dust, researchers can infer the composition, density, and temperature of these regions. This technique has provided valuable information about the early universe, revealing details about the formation of galaxies and the evolution of cosmic structures. The impact of black hole jets extends beyond their scientific significance. They also captivate the human imagination. The sheer scale and power of these phenomena challenge our perceptions of reality, reminding us of the vastness and complexity of the cosmos. They serve as a testament to the incredible forces at work in the universe, forces that operate on scales far beyond human comprehension. Images of jets stretching across millions of light years evoke a sense of wonder, inspiring us to ask profound questions about our place in the universe. At the same time, black hole jets raise philosophical questions about the nature of existence. They are a stark reminder of the extremes that nature can reach, where time and space behave in ways that defy intuition. These jets, born from regions where gravity is so intense that not even light can escape, challenge our understanding of the universe's fundamental laws. They prompt us to consider the boundaries of human knowledge and the possibilities that lie beyond. As our understanding of black hole jets continues to grow, so too does our appreciation for the intricate tapestry of the universe. These cosmic particle accelerators are not just isolated phenomena. They are deeply interconnected with the broader dynamics of galaxies, stars, and the cosmic web. They remind us that the universe is a dynamic, ever-changing place, shaped by forces both visible and invisible. In the coming decades, advances in technology and collaboration will likely lead to new breakthroughs in our understanding of black hole jets. From next-generation telescopes to innovative data analysis techniques, the tools at our disposal are expanding at an unprecedented pace. As we uncover more about these extraordinary phenomena, we will not only gain insights into the workings of the cosmos but also deepen our appreciation for the beauty and complexity of the universe. The story of black hole jets is far from complete. With each discovery, we are reminded of the vastness of the unknown and the boundless potential of human curiosity. These jets, blazing across the cosmos, serve as beacons of exploration, guiding us toward a deeper understanding of the universe and our place within it. The ongoing study of black hole jets is a testament to human ingenuity and the insatiable desire to understand the cosmos. Each observation, theoretical model, and experiment builds upon centuries of astronomical discovery, bridging the gap between the visible and invisible aspects of the universe. As technology evolves, so does our capacity to probe deeper into the mysteries of these extraordinary structures. One of the most revolutionary tools in the study of black hole jets has been very long baseline interferometry, VLBI. This technique combines observations from radio telescopes spread across the globe to create a virtual telescope with an effective diameter equal to Earth's size. VLBI has been instrumental in achieving extremely high-resolution images of black hole jets, including groundbreaking captures like the Event Horizon Telescope's image of the black hole in the galaxy M87. These images not only provide visual confirmation of theoretical predictions but also open new doors for studying the physics of jet formation and propagation. In particular, the image of M87's black hole revealed the bright ring of emission surrounding the event horizon and hinted at the base of the relativistic jet. These observations offer a rare glimpse into the region where the jet is born, allowing scientists to refine their models of how magnetic fields and plasma interact in the vicinity of a black hole. Future observations with even higher resolution could reveal more about the initial collimation and acceleration of jets, shedding light on processes that remain poorly understood. The ability to study black hole jets across multiple wavelengths is another critical advancement. Jets emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, each revealing different aspects of their structure and behavior. For instance, radio observations often show the large-scale morphology of jets, including their lobes and hotspots, while X-ray and gamma-ray observations probe the most energetic regions, where particles are accelerated to nearly the speed of light. By combining data from telescopes like the Chandra X-ray Observatory, the Hubble Space Telescope, and ground-based radio arrays, astronomers can construct a more complete picture of these phenomena. Additionally, polarization studies have become an invaluable tool for understanding the magnetic fields within jets. Polarized light carries information about the orientation and strength of magnetic fields, which are thought to play a crucial role in shaping and stabilizing jets. Recent observations have revealed highly ordered magnetic fields near the base of jets, supporting theories that these fields are responsible for collimating and accelerating the plasma. However, further research is needed to determine how these magnetic fields are generated and sustained, as well as how they interact with the black hole's spin and accretion disk. Theoretical simulations have also made significant contributions to our understanding of black hole jets. Using supercomputers, scientists can create detailed models of the extreme environments near black holes, incorporating the effects of relativity, magnetohydrodynamics, and radiation. These simulations allow researchers to test different scenarios and compare the results with observations, helping to refine our understanding of jet formation and dynamics. For example, simulations have shown that the interplay between the accretion disk and the black hole's magnetic field can produce jets with a wide range of properties, depending on factors like the black hole's spin and the rate of accretion. One area where simulations have been particularly illuminating is the study of jet interaction with surrounding environments. When jets encounter interstellar or intergalactic gas, they can create shock waves that compress and heat the gas, forming structures like radial lobes and hotspots. These interactions are not only visually striking but also play a key role in galaxy evolution. By simulating these processes, researchers can better understand how jets influence star formation, gas distribution, and the overall dynamics of galaxies. The relationship between black hole jets and galaxy clusters is another fascinating area of study. In clusters of galaxies, jets from supermassive black holes can regulate the temperature and density of the intra-cluster medium, a hot, diffuse gas that pervades the space between galaxies. By injecting energy into this medium, jets prevent it from cooling and collapsing, a process known as radio mode feedback. This feedback mechanism is crucial for explaining why some massive galaxies appear to have stopped forming stars, despite having abundant gas reserves. Observations of clusters like the Perseus and Virgo clusters have provided compelling evidence of this feedback, including spectacular images of cavities and ripples in the intra-cluster medium caused by jet activity. As we continue to study black hole jets, new questions and challenges arise. For example, recent observations have revealed that some jets exhibit helical or corkscrew-like structures, suggesting that they may be precessing or wobbling over time. This behavior could be caused by interactions with a companion black hole in a binary system, or by instabilities within the jet itself. Understanding these dynamics could provide insights into the history and environment of the black hole, as well as the broader context of its host galaxy. Another intriguing area of research is the potential connection between black hole jets and fast radio bursts, FRBs, mysterious millisecond-long pulses of radio waves observed from distant galaxies. Some theories suggest that FRBs could be associated with black hole activity, perhaps arising from interactions between jets and surrounding material. While this idea is still speculative, it highlights the potential for black hole jets to play a role in some of the universe's most enigmatic phenomena. Finally, the study of black hole jets has implications beyond astrophysics, touching on fundamental questions about the nature of spacetime, gravity, and quantum mechanics. For instance, the extreme conditions near a black hole's event horizon provide a natural laboratory for testing theories of quantum gravity, which seek to reconcile general relativity with quantum mechanics. By studying the radiation emitted by jets and their interaction with the black hole's magnetic field, scientists hope to uncover clues about the behavior of matter and energy in these exotic environments. Black hole jets are a reminder of the boundless complexity and beauty of the universe. They challenge us to push the limits of our understanding, inspiring awe and curiosity as we explore the cosmos. As we continue to unravel their mysteries, these cosmic particle accelerators will undoubtedly remain at the forefront of astrophysical research, guiding us toward new discoveries and deeper insights into the nature of reality itself. The enigmatic nature of black hole jets continues to spark curiosity and drive the quest for understanding one of the universe's most complex phenomena. As we delve further, we uncover how these jets act as both destroyers and creators, shaping galaxies and driving cosmic evolution. Their intricate processes not only redefine what we know about black holes but also open new possibilities for how energy and matter interact on the grandest scales. One of the emerging frontiers in the study of black hole jets is their role in transporting energy across intergalactic distances. When jets eject material at nearly the speed of light, they carry immense amounts of energy away from the black hole's vicinity. This energy influences vast regions of space, creating cavities, shock fronts, and even magnetic fields that stretch across millions of light years. Observations have shown that the energy carried by jets can regulate the temperature and pressure of intergalactic gas, preventing it from collapsing under gravity. This mechanism, known as feedback, helps maintain the delicate balance necessary for the stability of large-scale cosmic structures. Feedback mechanisms involving black hole jets also have profound implications for the life cycle of galaxies. Without the presence of jets, the gas within galaxies might cool too quickly, leading to runaway star formation. Instead, jets inject heat into the gas, slowing down this process and creating a more gradual and sustainable formation of stars. This regulation helps explain the observed distribution of galaxy types in the universe, particularly the prevalence of massive elliptical galaxies that appear to have exhausted their star-forming potential. The interaction between jets and interstellar gas also creates visually stunning phenomena. As jets plow through their surroundings, they generate shock waves that compress the gas into intricate structures, including filaments, bubbles, and rings. These features are not just beautiful, they serve as records of the jet's power and history. For example, the iconic radio lobes, seen in some galaxies, mark the regions where jets have deposited their energy over millions of years. By studying these structures, astronomers can trace the activity of supermassive black holes across cosmic time. Additionally, the ability of jets to transfer angular momentum has significant consequences for the evolution of black holes and their surrounding systems. When material falls into a black hole, it often carries angular momentum that must be shed before the material can cross the event horizon. Jets provide a mechanism for this process, acting as a kind of cosmic exhaust system that expels excess energy and angular momentum. This interplay between accretion and jet formation determines how quickly black holes grow, influencing their mass and spin. As researchers explore these dynamics, they increasingly rely on advanced computational models to simulate the conditions near black holes. Simulations allow scientists to test various scenarios, such as how changes in the magnetic field strength or accretion rate affect jet properties. These models have revealed that jets are remarkably sensitive to their initial conditions, meaning that even small variations in the environment can lead to dramatically different outcomes. For instance, changes in the alignment between a black hole's spin axis and its accretion disk can produce jets with different orientations and structures. These insights are particularly relevant for understanding the jets associated with binary black hole systems. In such systems, the gravitational influence of a second black hole can introduce complex dynamics, causing the primary black hole's accretion disk to warp or precess. This behavior, in turn, affects the direction and stability of the jet, creating patterns that can be observed across large distances. The study of binary black hole jets is still in its early stages, but it promises to provide new perspectives on how black holes interact with their environments and with each other. The connection between black hole jets and cosmic rays is another area of active investigation. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, and they are thought to originate from various astrophysical sources, including black hole jets. Observations suggest that the intense magnetic fields within jets can accelerate particles to extreme energies, making them some of the most efficient particle accelerators in the universe. By studying the composition and energy spectrum of cosmic rays, scientists hope to identify signatures that point back to black hole jets as their source. Moreover, the study of jets is increasingly relevant to the search for extraterrestrial life. In some cases, jets can sterilize regions of space by bombarding planets and moons with high-energy radiation. However, they can also trigger the formation of stars and planetary systems by compressing interstellar gas. Understanding these dual effects is crucial for assessing the habitability of exoplanets and the broader conditions for life in the universe. Despite these advances, many questions about black hole jets remain unanswered. For example, while we have a general understanding of how jets are launched, the details of the underlying mechanisms are still debated. Are jets primarily driven by the rotational energy of the black hole, as proposed by the Blandford's-Nagic mechanism, or by the thermal energy of the accretion disk? Or do both processes work together in some yet-to-be-discovered way? Resolving these questions will require a combination of observational, theoretical, and experimental approaches, pushing the limits of current technology and imagination. Another enduring mystery is the role of black hole spin in jet formation. Observations suggest that the most powerful jets are associated with rapidly spinning black holes, but the exact relationship between spin and jet strength is not fully understood. Measuring the spin of black holes is itself a challenging task, requiring indirect methods such as analyzing the shape of X-ray emission lines or modeling the dynamics of accretion disks. As techniques improve, they may provide new clues about how spin influences jet production and energy output. Looking ahead, the future of black hole jet research is incredibly promising. Next-generation observatories, such as the James Webb Space Telescope and the Square Kilometre Array, will provide unprecedented sensitivity and resolution, enabling us to study jets in greater detail than ever before. These instruments will also allow astronomers to observe jets at earlier stages of the universe, offering insights into how black holes and galaxies co-evolved over cosmic history. In parallel, advancements in artificial intelligence and machine learning are revolutionizing data analysis, making it possible to process the enormous volumes of information generated by modern telescopes. These tools are helping researchers identify subtle patterns and anomalies in jet behavior, uncovering new phenomena that might otherwise go unnoticed. As our ability to observe and analyze jets continues to grow, so too does our potential to unlock their secrets. The study of black hole jets is a journey into the heart of the unknown, where the laws of physics are stretched to their limits. It is a field that challenges us to think beyond the boundaries of our current understanding, inspiring a sense of wonder and curiosity that drives scientific discovery. With each new observation and theory, we come closer to unraveling the mysteries of these cosmic particle accelerators, illuminating not only the nature of black holes but also the fundamental workings of the universe itself. The significance of black hole jets extends beyond their direct effects on galaxies and cosmic structures. They also provide a unique opportunity to study fundamental physics under extreme conditions. Near the base of a jet, the environment around a black hole becomes a natural laboratory where gravity, magnetism, and quantum mechanics interact in ways that are difficult, if not impossible, to replicate on Earth. By studying jets, scientists can test theories about the behavior of matter and energy in the most extreme regimes known to science. One key aspect of this research involves understanding the plasma dynamics within jets. Plasma is a highly energized state of matter consisting of charged particles, and it is the primary medium through which jets transport energy. The behavior of plasma in such environments is governed by a combination of magnetic fields, relativistic speeds, and intense radiation. These interactions lead to phenomena such as magnetic reconnection, where magnetic field lines break and reconnect, releasing enormous amounts of energy. Magnetic reconnection is thought to play a crucial role in accelerating particles within jets, making it a critical area of study. Additionally, black hole jets allow us to investigate the effects of relativistic beaming. Relativistic beaming occurs when particles moving at nearly the speed of light emit radiation that is highly concentrated in the direction of their motion. This effect makes jets appear much brighter when viewed head-on, an observation bias that astronomers account for when studying their properties. Relativistic beaming also provides insights into the velocities of particles within jets, offering clues about the mechanisms driving their acceleration. The study of black hole jets also contributes to our understanding of cosmic magnetic fields. Magnetic fields are essential for the formation and stability of jets, as they guide the flow of plasma and help launch material away from the black hole. Observations suggest that these fields are twisted into helical structures, creating a corkscrew pattern that can be detected in polarized light. By analyzing the polarization of radiation emitted by jets, astronomers can map the geometry and strength of these magnetic fields, shedding light on their role in jet formation and stability. Another intriguing aspect of black hole jets is their connection to gamma-ray bursts, GRBs. GRBs are among the most energetic events in the universe, releasing as much energy in a few seconds as the Sun will emit over its entire lifetime. Some GRBs are believed to originate from the collapse of massive stars into black holes, a process that also produces relativistic jets. These jets are thought to emit gamma rays as they interact with surrounding material, providing a potential link between GRBs and the jets observed in active galaxies. By comparing the properties of these phenomena, scientists aim to uncover commonalities that may reveal the underlying physics. The observational study of black hole jets has been greatly enhanced by multi-wavelength astronomy. Jets emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, each revealing different aspects of their structure and behavior. For example, radio observations can trace the large-scale morphology of jets, while X-ray and gamma-ray data provide insights into their high-energy processes. Combining data from multiple wavelengths allows astronomers to construct a more complete picture of jets, from their origins near the black hole to their interactions with the surrounding environment. Moreover, the use of interferometry has revolutionized the imaging of black hole jets. Interferometry involves combining signals from multiple telescopes to achieve the resolution of a much larger instrument. This technique was famously used to capture the first image of a black hole's event horizon, and it continues to play a vital role in studying jets. With interferometric arrays such as the Very Long Baseline Array, VLBA, and the Event Horizon Telescope, EHT, astronomers can resolve fine details in jets, including their internal structures and the regions where they connect to the accretion disk. Theoretical models of black hole jets are also advancing rapidly, driven by improvements in computational power and numerical techniques. General relativistic magnetohydrodynamics, GRMHD, simulations, which combine Einstein's theory of general relativity with the principles of magnetohydrodynamics, are now capable of modeling the complex interactions that govern jet formation. These simulations have provided valuable insights into the conditions near black holes, including the role of frame dragging, a relativistic effect where the rotation of a black hole twists spacetime itself. One of the most ambitious goals in this field is to determine how jets affect the long-term evolution of the universe. By regulating star formation and redistributing matter and energy, jets play a role in shaping the large-scale structure of the cosmos. They may even influence the distribution of dark matter, the mysterious substance that makes up most of the universe's mass. Understanding these connections requires integrating observations of jets into larger cosmological models, a challenge that is pushing the boundaries of astrophysics. As we consider the broader implications of black hole jets, it is worth reflecting on their philosophical significance. These jets, born from some of the most destructive forces in the universe, are also agents of creation and transformation. They exemplify the duality of nature, where destruction and creation are intertwined in a delicate balance. Studying jets reminds us of the interconnectedness of all things, from the smallest particles to the largest galaxies, and it inspires a sense of awe at the complexity and beauty of the cosmos. The journey to understand black hole jets is far from over. Each new discovery raises new questions, challenging us to think deeper and reach further. With the rapid pace of technological and theoretical advancements, the next few decades promise to be a golden age for jet research. From unveiling the secrets of particle acceleration to exploring their role in cosmic evolution, black hole jets remain one of the most captivating mysteries of the universe. The quest to unravel the mysteries of black hole jets continues to drive innovation in both observational astronomy and theoretical physics. As we refine our tools and models, we are beginning to piece together a more detailed understanding of how these cosmic particle accelerators operate. Yet, the vastness and complexity of the universe ensure that every answer reveals new puzzles, making black hole jets a continually evolving frontier in astrophysics. One of the most compelling questions in jet research is how the matter falling into a black hole, a seemingly chaotic and violent process, leads to the formation of highly ordered, relativistic jets. The consensus is that the interaction between the black hole's intense gravitational field and its magnetic environment plays a critical role. However, the exact mechanisms remain elusive. Observations suggest that not all black holes produce jets, prompting researchers to explore what specific conditions are necessary for their formation. The spin of the black hole, the composition of the accretion disk, and the structure of the surrounding magnetic field are all suspected to be key factors. To better understand these conditions, scientists rely on high-resolution simulations. These simulations incorporate the laws of physics under extreme conditions, including general relativity and magnetohydrodynamics. By modeling the dynamics of accretion disks and magnetic fields, researchers can test various hypotheses about jet formation. For instance, one prominent theory is the Blandford's-Nagic mechanism, which proposes that jets are powered by the rotational energy of a spinning black hole. This energy is extracted via magnetic fields anchored in the accretion disk, effectively launching jets at relativistic speeds. Another area of active research involves the role of feedback mechanisms in shaping galaxies and clusters. Black hole jets are thought to regulate star formation by heating and expelling gas, but the specifics of this process depend on the interplay between the jets and the surrounding medium. Observations of galaxy clusters have revealed vast cavities carved out by jets, often spanning hundreds of thousands of light-years. These cavities are filled with hot, X-ray emitting gas, suggesting that the energy released by jets is sufficient to counteract the gravitational pull of the cluster, preventing gas from cooling and condensing into stars. The interplay between jets and the intergalactic medium also affects the distribution of metals in the universe. Metals, in the astrophysical sense, refer to elements heavier than helium, which are produced in the cores of stars and distributed through processes like supernova explosions. Black hole jets can transport these metals across vast distances, enriching the intergalactic medium and influencing the chemical evolution of galaxies. Understanding this process requires detailed studies of jet composition, as well as their interactions with surrounding gas. At smaller scales, black hole jets provide a unique laboratory for studying particle physics. The extreme conditions within jets allow particles to reach energies far beyond what can be achieved in human-made accelerators like the Large Hadron Collider. These high-energy particles emit synchrotron radiation as they spiral along magnetic field lines, producing a characteristic spectrum that can be observed across multiple wavelengths. By analyzing this radiation, scientists can infer the properties of the particles and the mechanisms that accelerate them to such incredible speeds. One of the most enigmatic aspects of jet physics is the process of particle acceleration itself. While it is clear that magnetic fields and relativistic shocks play a role, the details are still debated. Some theories propose that turbulence within the jet creates pockets of magnetic reconnection, where field lines snap and reconnect, releasing bursts of energy that accelerate particles. Others suggest that shocks generated by variations in jet velocity provide the necessary conditions. Differentiating between these scenarios requires not only detailed observations but also advanced simulations that can replicate the chaotic environment within jets. The study of black hole jets is also pushing the boundaries of observational technology. Instruments like the Chandra X-ray Observatory, the Hubble Space Telescope, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided unprecedented views of jets, revealing details about their structure, composition, and interactions with their environment. Future telescopes, such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, promise to expand our capabilities even further. These instruments will allow us to observe jets in greater detail and at higher resolutions, potentially uncovering new phenomena. In addition to traditional telescopes, astronomers are increasingly relying on multimessenger astronomy to study black hole jets. This approach combines data from electromagnetic radiation, gravitational waves, and neutrinos to provide a more comprehensive view of astrophysical phenomena. For example, the detection of a neutrino originating from a blazar, a type of active galaxy with a jet pointed toward Earth, provided direct evidence linking jets to high-energy cosmic rays. Such discoveries highlight the potential of multimessenger astronomy to reveal new insights into the nature of jets and their role in the universe. As we look to the future, the study of black hole jets is likely to intersect with other fields of research, including dark matter and dark energy. Some theories suggest that jets could provide indirect evidence for the existence of dark matter, either through their gravitational effects or by serving as sites for dark matter interactions. Similarly, the energy released by jets may influence the large-scale structure of the universe, offering clues about the mysterious force driving its accelerated expansion. The mysteries of black hole jets also have profound implications for our understanding of the universe's origins and ultimate fate. By studying the most extreme environments in the cosmos, we gain insights into the fundamental laws that govern matter, energy, and spacetime. These insights not only deepen our appreciation for the complexity of the universe but also challenge us to rethink our place within it. Black hole jets serve as a reminder of the boundless curiosity that drives scientific exploration. They are a testament to humanity's ability to grapple with the unknown, to seek answers to questions that stretch the limits of our understanding. As we continue to probe the secrets of these cosmic particle accelerators, we are not only expanding our knowledge of the universe but also uncovering new ways to marvel at its beauty and complexity. The intricate dance of black hole jets, their formation, propagation, and impact, is a narrative that spans the fabric of spacetime itself. These relativistic jets are not mere phenomena. They are cosmic storytellers, revealing the interplay between matter and energy under the universe's most extreme conditions. As the story unfolds, we encounter even more questions and astonishing connections to fundamental physics and cosmological evolution. One particularly fascinating aspect is the symmetry, or sometimes lack thereof, exhibited by jets. Many active galactic nuclei (AGN) with jets show a twin-beam structure, emanating in opposite directions from the poles of the black hole. Yet, these beams often appear asymmetric in observational data. This asymmetry is not inherent to the jets themselves but is attributed to relativistic effects. The jet moving toward us appears brighter because its emission is relativistically beamed, a phenomenon called Doppler boosting. Meanwhile, the counterjet moving away seems dimmer or even invisible due to the same effect. This contrast underscores how relativity permeates the universe on all scales, from quantum particles to the dynamics of galaxies. Another enigma lies in the collimation of jets, or how they maintain their narrow, focused shape over such vast distances. In theory, without sufficient containment mechanisms, the energy and matter within jets would dissipate into the surrounding medium. However, observations consistently show jets retaining their structure across intergalactic scales. Magnetic fields are again suspected to play a pivotal role, acting as cosmic scaffolding that channels and constrains the plasma flow. The helical, twisted nature of these fields, often referred to as magnetic flux tubes, is believed to stabilize the jets and guide their trajectory. As the jets traverse space, they interact with the interstellar and intergalactic medium. These interactions are far from passive. When jets plow through the gas and dust in their path, they generate shock waves that compress and heat the surrounding material. This process can trigger star formation by creating dense regions where gravitational collapse becomes inevitable. Paradoxically, the same jets can also suppress star formation by blowing gas out of galaxies, reducing the raw material available for stars. This dual role underscores the complexity of jet feedback mechanisms and their profound influence on galactic evolution. One particularly striking example of jet feedback is the phenomenon known as radial lobes. As jets decelerate and deposit their energy into the surrounding medium, they inflate colossal, bubble-like structures visible in radio wavelengths. These lobes can span millions of light years, serving as a testament to the immense power unleashed by jets. The energy within these lobes can remain trapped for billions of years, influencing the dynamics of galaxy clusters long after the jets themselves have faded. The energy spectrum of particles within jets is another area of intense study. The particles emit radiation across the electromagnetic spectrum, from radio waves to gamma rays. By analyzing this radiation, astronomers can infer the energy distribution of particles, revealing clues about the acceleration mechanisms at play. For instance, the observation of ultra-high-energy cosmic rays originating from AGN jets poses a significant challenge to existing models. These particles have energies millions of times higher than those produced in terrestrial accelerators, raising questions about the physical processes capable of such acceleration. High-energy neutrinos, another byproduct of jet activity, offer additional insights. Neutrinos are elusive particles that rarely interact with matter, making them difficult to detect but invaluable for probing the universe's most energetic phenomena. The detection of a high-energy neutrino in coincidence with a blazar flare marked a milestone in multimessenger astronomy, directly linking jets to neutrino production. This discovery not only confirmed theoretical predictions but also opened a new window for studying the universe. The environment surrounding jets is equally intriguing. Accretion disks, composed of matter spiraling into the black hole, are the primary fuel source for jets. These disks are incredibly hot, emitting light across multiple wavelengths, and their dynamics are governed by complex interactions between gravity, magnetic fields, and turbulence. The interplay between the disk and the jet is a dynamic feedback loop, with the jet's magnetic fields influencing the flow of matter within the disk and vice versa. Adding another layer of complexity is the role of the black hole's spin. Faster spinning black holes are thought to produce more powerful jets, as their rotational energy contributes to the jet's propulsion. This relationship, known as the spin-jet coupling, suggests that the history of a black hole's spin evolution, shaped by mergers and accretion events, could determine the properties of its jets. Observing these correlations provides a way to trace the life history of black holes and their host galaxies. On the cosmological scale, jets act as cosmic lighthouses, allowing astronomers to probe the distant universe. Quasars, the most luminous type of AGN, are powered by jets and can be seen across billions of light years. Their light carries information about the conditions of the early universe, including the composition and structure of the intergalactic medium. By studying quasars, we gain insights into the universe's formative years and the role jets played in shaping it. Jets also serve as natural laboratories for testing the limits of fundamental physics. Their extreme conditions, high densities, strong magnetic fields, and near-light speeds, recreate environments that cannot be achieved on Earth. These conditions make jets an ideal testing ground for theories of quantum gravity, particle physics, and relativity. For instance, observing the behavior of particles in jets can provide clues about the unification of forces at high energies, a long-sought goal in physics. The continued study of black hole jets is a testament to human ingenuity and curiosity. As technology advances, we are poised to uncover even more about these enigmatic structures. Instruments like the Event Horizon Telescope, which captured the first-ever image of a black hole, are being adapted to study jet formation in unprecedented detail. Meanwhile, space-based observatories like the upcoming Athena X-ray Observatory promise to shed light on the interactions between jets and their environments. Despite our progress, many mysteries remain. Why do some black holes produce jets while others do not? What determines the direction and stability of jets over time? How do jets influence the long-term evolution of galaxies and clusters? These questions remind us that the universe is a vast and dynamic place, full of surprises waiting to be discovered. As we continue to explore the cosmos, black hole jets remain one of the most compelling subjects in astrophysics. They challenge our understanding of the universe, push the boundaries of technology, and inspire us to look deeper into the unknown. In their blinding brilliance and unfathomable power, they are both a scientific puzzle and a source of wonder, inviting us to ponder the infinite complexities of the universe. The study of black hole jets has evolved into one of the most multifaceted disciplines in modern astrophysics, intertwining with almost every branch of the field. These jets are not just explosive phenomena. They are key players in a larger cosmic narrative. They have become tools for unlocking secrets about the birth of galaxies, the dynamics of cosmic voids, and even the nature of spacetime itself. Their study is as much about understanding the forces that govern our universe as it is about deciphering their origins. One critical mystery surrounding jets is the dichotomy in their formation. Not all black holes emit jets, even when actively accreting matter from a surrounding disk. This discrepancy suggests that the conditions for jet formation are more specific and complex than initially thought. Observations reveal that only certain types of black holes, often characterized by rapid spin and strong magnetic fields, produce powerful, collimated jets. This selectivity raises questions about the relationship between the black hole's properties and the surrounding environment. Is it the mass, the spin, or the composition of the accreting material that determines whether jets are launched? Or is it a combination of these factors? The spin of a black hole, as mentioned earlier, plays a pivotal role. Theoretical models suggest that rapidly spinning black holes can tap into their rotational energy to power jets, a process described by the Blandford's-Nagic mechanism. In this model, the magnetic fields threading the black hole's event horizon extract energy from the black hole's spin, converting it into the kinetic and electromagnetic energy of the jet. However, the exact details of this energy extraction remain unclear. Are the magnetic fields generated by the accretion disk, or do they originate from the interstellar medium? And how do these fields become so precisely aligned with the black hole's spin axis? Magnetic reconnection, a process where magnetic field lines break and reconnect, is another suspected jet driver. This phenomenon, observed in solar flares and Earth's magnetosphere, could also occur in the extreme environments around black holes. Reconnection would release tremendous amounts of energy, accelerating particles to near-light speeds and launching them along the magnetic field lines. If this process is indeed central to jet formation, it would provide a universal mechanism linking jets to other astrophysical phenomena involving magnetic fields. As jets propagate through space, their interactions with the surrounding medium produce a cascade of observable effects. These interactions are not just byproducts but are often critical to the evolution of the host galaxy and its neighbors. For example, jets can clear out vast amounts of gas from a galaxy's central regions, effectively quenching star formation. This process, known as AGN feedback, is a cornerstone of modern galaxy evolution models. It helps explain why massive galaxies today contain relatively little cold gas and why the most massive galaxies are often dormant in terms of star formation. On the other hand, jets can also stimulate star formation under the right conditions. By compressing gas clouds in their path, jets can trigger gravitational collapse, leading to the birth of new stars. This dual role, both destructive and constructive, makes jets a fascinating example of nature's ability to balance creation and destruction. Understanding this balance is crucial for developing accurate models of galaxy formation and evolution. Jets also illuminate the large-scale structure of the universe. As they interact with the intergalactic medium, jets create vast bubbles and cavities visible in X-ray and radio wavelengths. These structures, often spanning hundreds of thousands of light-years, are like footprints left by the jets, revealing their journey through space. The energy injected by jets into these regions prevents gas from cooling and forming stars, influencing the dynamics of galaxy clusters. This feedback loop, extending across millions of light-years, demonstrates the far-reaching influence of black hole jets. Interestingly, the influence of jets is not confined to the observable universe. They also serve as natural laboratories for testing fundamental physics. For example, the extreme conditions within jets provide a unique setting to study plasma physics, high-energy particle interactions, and even quantum field theory. These conditions are impossible to replicate on Earth, making jets invaluable for exploring the universe's most extreme phenomena. Jets also offer insights into the enigmatic nature of dark matter and dark energy. While not directly related to these mysterious components of the universe, the distribution and behavior of jets can serve as indirect probes. For instance, the way jets interact with the intergalactic medium can reveal the density and composition of matter in their vicinity, providing clues about dark matter's distribution. Similarly, the large-scale effects of jet activity on galaxy clusters could offer hints about the influence of dark energy on cosmic expansion. In recent years, advances in observational technology have opened new frontiers in jet research. High-resolution imaging from instruments like the Very Long Baseline Array, VLBA, and the Event Horizon Telescope, EHT, has provided unprecedented views of jet structures. These observations have confirmed theoretical predictions while also revealing unexpected complexities, such as helical patterns and internal shocks within jets. Meanwhile, Space-based observatories like the Fermi Gamma Ray Space Telescope have detected high-energy emissions from jets, offering new perspectives on their particle acceleration mechanisms. Multimessenger astronomy, which combines observations of electromagnetic radiation, gravitational waves, and neutrinos, has further enriched our understanding. The detection of high-energy neutrinos from a blazar, an AGN with a jet pointed directly at Earth, marked a significant breakthrough. It confirmed that jets are capable of accelerating particles to energies sufficient to produce neutrinos, linking jet activity to the most energetic processes in the universe. Despite these advances, many mysteries remain. For example, the origin of ultra-high-energy cosmic rays, some of which are believed to come from jets, is still debated. How do jets accelerate particles to such extreme energies, far beyond what human-made accelerators can achieve? And why do some jets appear stable and focused while others are chaotic and turbulent? The answers to these questions are not just academic. They have profound implications for our understanding of the universe's fundamental forces and the interplay between matter, energy, and spacetime. Jets challenge our preconceptions and push the boundaries of what we know, serving as both a source of wonder and a call to deeper inquiry. As we continue to explore the cosmos, black hole jets remain a testament to the power of human curiosity and ingenuity. They remind us that even in the face of the universe's vastness and complexity, we have the tools and the will to seek answers. And in doing so, we uncover not just the secrets of the cosmos but also the infinite potential of the human mind. The mysteries of black hole jets stretch far beyond their immediate impact on galaxies and the larger universe. These cosmic accelerators are key to some of the most fundamental questions in astrophysics, from the nature of black holes to the behavior of matter under extreme conditions. While much has been discovered, each new finding often leads to even deeper and more profound questions. One area of growing interest is the role of black hole jets in the formation of supermassive black holes. These behemoths reside at the centers of most galaxies, and their growth and evolution have long been a topic of speculation. Jets may play a crucial role in the growth of these supermassive black holes, especially in the early stages of galaxy formation. During this period, the black hole's accretion disk would be feeding it large amounts of matter. The energy and material ejected in the form of jets could significantly alter the dynamics of the surrounding galaxy, impacting the growth of the black hole itself. This interplay between the black hole and its host galaxy could also influence the formation of other celestial bodies in the region, such as stars, planets, and even other black holes. While much of the focus has been on the dramatic visible effects of black hole jets, their less obvious, underlying mechanisms are equally intriguing. One of the most puzzling aspects of these jets is how they can maintain their coherence and direction over vast distances. Despite the chaotic and turbulent environments through which they pass, black hole jets can travel millions of light-years without losing their structure. This level of persistence is far beyond the capabilities of typical particle outflows in other environments, where turbulence and collisions usually cause disruptions. Researchers suspect that magnetic fields play a central role in this phenomenon. These magnetic fields may serve as a kind of guiding mechanism, keeping the particles in the jet aligned and preventing them from scattering. This idea ties into the concept of magnetic confinement, which is also used in fusion reactors here on Earth to control plasma. In the case of black hole jets, the magnetic fields threading through the jets and surrounding space could be shaped by the black hole's spin, further reinforcing the coherency and stability of the jet's structure. One of the most awe-inspiring characteristics of black hole jets is the incredible speeds at which they operate. The matter expelled by these jets often travels at relativistic speeds, close to the speed of light. As particles in the jet reach these velocities, their kinetic energy becomes immense. This means that jets can carry an extraordinary amount of energy across vast distances, impacting everything in their path. This is why the study of black hole jets is not just important for understanding the mechanics of black holes, but also for understanding the broader dynamics of galactic evolution and cosmic structure. Relativistic jets are not only fascinating for their sheer scale and power, they also present some of the most extreme environments in the universe. The energy within these jets is so high that it accelerates particles to near-light speeds, creating powerful radiation emissions that span the entire electromagnetic spectrum. These emissions include everything from radio waves to X-rays, and in some cases, even gamma rays. This wide range of radiation makes black hole jets not only key players in the understanding of high-energy astrophysics, but also an important part of the broader cosmic feedback loop. For example, some of the highest energy gamma rays detected by space telescopes come from blazars, active galactic nuclei, AGN, with jets pointing directly at Earth. These gamma ray emissions provide vital clues about the inner workings of black holes, as well as the physical processes occurring within the jets themselves. The study of these high-energy emissions is crucial for our understanding of the universe, as they can reveal the nature of the most energetic phenomena in existence. As these jets traverse vast expanses of intergalactic space, they also interact with surrounding matter, providing clues about the large-scale structure of the universe. A significant mystery surrounding these jets is the question of how they produce such high-energy particles in the first place. The physics of particle acceleration is complex and still largely theoretical in the context of black holes. Various models suggest that the energy responsible for accelerating particles to relativistic speeds is drawn from a variety of sources, including the black hole's spin and the accretion disk. But how these processes work together to create the jet's powerful emissions is not fully understood. Some theories propose that the energy of the black hole itself is used to accelerate particles, while others suggest that shock waves in the jets could be responsible for producing the high-energy radiation. In addition to these fundamental questions, there are more specific mysteries about the structure of jets themselves. Some jets appear to be highly collimated, or narrow, while others are more diffuse and spread out. The reasons behind these differences are not fully clear. It could be that the properties of the surrounding medium, such as the density of gas or the presence of magnetic fields, affect the way the jets evolve. Alternatively, the structure of the jet could depend on the rate at which matter is being accreted by the black hole, or the orientation of the black hole's spin axis relative to the jet. These factors could all contribute to the variability in the appearance and behavior of black hole jets. Another area of intrigue involves the detection of high-energy neutrinos from blazars. These neutrinos are thought to be produced in the most extreme environments surrounding black holes. Detecting these elusive particles opens up an entirely new window into the study of black hole jets. Neutrinos are incredibly difficult to detect due to their weak interactions with matter, but recent breakthroughs in neutrino observatories like the IceCube Neutrino Observatory in Antarctica have provided valuable insights. By detecting neutrinos from distant galaxies, scientists can indirectly study the high-energy processes occurring in the vicinity of black holes. The study of black hole jets is also instrumental in understanding how these jets influence their host galaxies. In some cases, the energy released by jets can trigger massive starbursts, rapidly increasing the rate of star formation in the galaxy. In other instances, the jets can suppress star formation by heating up the surrounding gas, preventing it from cooling and collapsing to form new stars. This delicate balance between creation and destruction highlights the role of black hole jets in shaping the larger-scale evolution of galaxies and the universe as a whole. The impact of these jets is not limited to individual galaxies. In galaxy clusters, jets can affect the entire cluster's evolution. These vast cosmic structures contain hundreds or even thousands of galaxies, and the jets from their central black holes can influence the behavior of the entire cluster. The energy expelled by these jets can prevent the cooling of gas within the cluster, which is crucial for the formation of new stars. This process, known as feedback, has profound implications for our understanding of how galaxy clusters evolve over cosmic time. Understanding the nature of black hole jets, then, is not just about understanding the black holes themselves but also about understanding the large-scale processes that govern the universe. From galaxy formation to the acceleration of particles to near-light speeds, black hole jets are central to some of the most fundamental questions in astrophysics. They remind us of the immense power and mystery of the universe, challenging our understanding of the physical laws that govern everything from the smallest particles to the largest cosmic structures. As our ability to observe and study these jets improves, we are likely to make even more groundbreaking discoveries. The future of black hole jet research promises to be just as exciting and filled with as many surprises as the past few decades have been. Each new discovery brings us closer to unraveling the complex interactions between black holes, their jets, and the galaxies they inhabit. And as we continue to probe deeper into the mysteries of the cosmos, we will undoubtedly uncover even more of the secrets hidden within these cosmic particle accelerators. The profound and powerful nature of black hole jets has left an indelible mark on our understanding of the cosmos. The question of how these jets affect their host galaxies, and even the very fabric of space itself, opens doors to entire new realms of exploration. For decades, we have marveled at the immense distances that these jets travel, often spanning millions of light years, and the extreme forces at play in their formation and propagation. Yet, even with all that we have learned, the mysteries of these cosmic outflows are far from being fully understood. One of the most tantalizing aspects of black hole jets is their connection to the process of feedback in galaxies. When considering the life cycle of a galaxy, it's important to understand how energy from supermassive black holes can regulate the formation of new stars. Black hole jets can either promote or suppress star formation depending on the environment they are in. The energy released by these jets, especially in the form of high-energy radiation and powerful winds, can heat up the gas surrounding a galaxy. If the gas becomes too hot, it is prevented from cooling down and collapsing, which is a necessary step for new stars to form. In this way, black hole jets can essentially stifle the creation of new stars, potentially halting the growth of a galaxy altogether. However, black hole jets can also have the opposite effect in some cases. In certain environments, the outflow of material can compress gas in a galaxy, triggering a burst of star formation. This phenomenon is particularly common in galaxies that are still in their formative stages, where jets can act as a catalyst for the birth of new stars by concentrating gas in specific regions. This starburst activity is another example of how black hole jets are not just destructive forces. They are part of a larger, more intricate process that dictates the evolution of galaxies. The role of black hole jets in galaxy evolution, though, is still not fully understood. While some researchers believe that jets have the power to shut down star formation in the long term, others argue that the jets could play a pivotal role in nurturing new stars in the early stages of a galaxy's life. The competing forces at play, heating versus cooling, destruction versus creation, are what make this topic so fascinating, and why it has become one of the central questions in astrophysical research. In a more large-scale context, black hole jets can have a significant influence on the evolution of galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies. Within these clusters, supermassive black holes typically sit at the center of each galaxy, spewing out relativistic jets that interact with the intergalactic medium, gas that fills the space between galaxies. These jets can have a profound impact on the cluster's overall behavior, preventing the gas from cooling and collapsing into new stars, thereby impacting the rate of star formation across the entire cluster. This phenomenon, known as feedback, is integral to understanding how galaxy clusters evolve over cosmic time. The feedback mechanisms driven by black hole jets are not limited to star formation alone. They can also have a significant impact on the growth and behavior of black holes themselves. For example, in some scenarios, the energy and matter ejected from a black hole's jet can help regulate the rate at which the black hole continues to accrete matter from its surrounding environment. This feedback process has been suggested to play a critical role in limiting the growth of supermassive black holes. Without such a regulatory mechanism, these black holes could theoretically continue to grow uncontrollably, accumulating vast amounts of mass over time. Furthermore, black hole jets also have the potential to shape the large-scale structure of the universe. The interaction between jets and the surrounding matter can lead to the formation of gigantic cavities in the intergalactic medium, regions where the gas has been heated and expelled by the energy released by the jets. These cavities, also called radio lobes, can extend millions of light-years in diameter and are often associated with powerful active galactic nuclei, AGN, and radio galaxies. By creating these large-scale structures, black hole jets may play a role in shaping the broader cosmic environment, influencing the distribution of matter in the universe, and possibly even affecting the formation of new galaxies and clusters. Despite all that we've discovered, the underlying mechanisms that drive the formation of black hole jets are still poorly understood. Theories abound, but the true nature of how these jets are launched and maintained is a subject of ongoing research. Most scientists agree that the process is tied to the interaction between the black hole's accretion disk, its surrounding magnetic fields, and the black hole's spin. However, how exactly these factors come together to produce the coherent, relativistic jets that we observe is still a matter of debate. Some of the leading theories suggest that the magnetic fields play a pivotal role in launching and collimating the jets. Magnetic fields are thought to be created as matter spirals in toward the black hole, generating enormous electromagnetic forces. These forces can then accelerate particles to relativistic speeds, expelling them along the black hole's rotational axis in the form of jets. The black hole's spin, its rotation around its axis, may also help to focus these jets, much like a rotating top spins more stably than a non-rotating one. However, the exact mechanism by which this works, and why some black holes produce powerful jets while others do not, is still one of the biggest unsolved mysteries in astrophysics. What is clear is that black hole jets are among the most extreme phenomena in the universe, capable of accelerating particles to speeds close to the speed of light and generating high-energy radiation across the entire electromagnetic spectrum. The fact that these jets can persist over vast distances, often spanning millions of light-years, further highlights the extraordinary power involved. Studying these jets not only offers insight into the behavior of black holes themselves but also into the broader forces that govern the universe, from galaxy formation to the acceleration of particles to near-light speeds. As we continue to study black hole jets, new advancements in technology, such as more powerful telescopes and space observatories, promise to unlock even more secrets. With instruments like the Event Horizon Telescope, which famously captured the first-ever image of a black hole's event horizon, researchers are now able to probe deeper into the heart of these cosmic engines. These new technologies will enable scientists to study black hole jets with unprecedented detail, shedding light on their formation, structure, and role in the universe. One exciting prospect is the potential to observe the switching on of black hole jets. Some black holes are thought to switch between active and quiescent phases, with jets appearing only during certain periods. Observing these transitions could offer crucial insights into the mechanisms behind jet formation and provide a more comprehensive understanding of black hole behavior over time. These observations could also help answer the lingering question of why some black holes produce powerful jets while others do not. Moreover, the continued study of the radiation emitted by black hole jets, particularly the high-energy gamma rays and neutrinos, may offer another crucial piece of the puzzle. These emissions provide a window into the most extreme environments in the universe, allowing scientists to probe the fundamental physics of black holes, accretion disks, and relativistic jets. As our understanding of these high-energy particles deepens, we may find new ways to unlock the mysteries of the universe, from the behavior of matter under extreme conditions to the ultimate fate of black holes themselves. Black hole jets represent one of the most fascinating and powerful phenomena in the cosmos. These relativistic outflows not only shape the galaxies and clusters they inhabit but also provide us with a deeper understanding of the fundamental forces that govern the universe. Whether it's the role of magnetic fields in jet formation, the impact of jets on galaxy evolution, or the mysteries of particle acceleration, black hole jets continue to challenge our understanding of the cosmos. As we continue to explore and study these cosmic particle accelerators, we are sure to uncover more profound mysteries that will reshape our view of the universe. The study of black hole jets is not just a tale of cosmic curiosity, but also one of technological innovation and the quest to understand the most extreme environments that nature has to offer. The interaction between black holes and the surrounding space is a dynamic and continually evolving subject, with discoveries happening at a fast pace. As the field of astrophysics progresses, more data becomes available, enabling scientists to form new theories, test old ones, and dive deeper into the mysteries of how these incredibly powerful jets are formed, what causes their variability, and how they influence the larger universe. One of the key reasons black hole jets are so intriguing to scientists is because they provide an opportunity to test the limits of our understanding of physics. The extreme conditions near a black hole, where gravity, magnetism, and the laws of motion interact in unimaginable ways, allow us to probe the limits of general relativity, quantum mechanics, and even the nature of spacetime itself. The jets act as laboratories of sorts, providing a unique setting in which we can study these fundamental forces at play. Relativity is particularly important in the study of black hole jets. According to Einstein's theory of general relativity, the intense gravitational pull of a black hole distorts the fabric of space and time. This warping creates some of the most bizarre and counterintuitive phenomena in the universe. As matter spirals into the black hole, the process of accretion creates a tremendous amount of heat, radiation, and angular momentum, which is channeled into the creation of relativistic jets. The fact that these jets can shoot out at speeds approaching the speed of light is a direct consequence of the relativistic effects at play in the vicinity of a black hole. Understanding how these jets are formed and how they behave offers critical insights into the nature of spacetime, the limits of speed, and the behavior of matter under extreme gravitational forces. The study of black hole jets also provides important clues about the behavior of magnetism on cosmic scales. As mentioned earlier, magnetic fields are thought to play a crucial role in the launching and collimation of jets. This magnetic field is generated by the accretion disk, material that is spiraling into the black hole, and the rotation of the black hole itself. The resulting electromagnetic forces are what propel the material at relativistic speeds, expelling it along the rotational axis of the black hole. This connection between magnetism and the formation of jets has led scientists to investigate the broader role that magnetic fields play in the universe, from their effects on galaxy formation to their role in the acceleration of cosmic rays. However, despite our increasing knowledge, the precise mechanics of how these jets form remain elusive. One of the primary challenges is the inability to directly observe the processes occurring at the very center of black holes. The extreme environment around the event horizon, where space-time becomes distorted beyond recognition, makes it difficult to gather observational data. Much of what we know about black hole jets comes from indirect observations, such as the detection of high-energy radiation, the mapping of the surrounding magnetic fields, and the observation of relativistic motions in the jets themselves. But the absence of direct observations presents a significant challenge in fully understanding how black hole jets are formed and how they evolve over time. As we continue to push the boundaries of our observational capabilities, however, new methods are emerging to help us probe the interiors of black holes and their jets in greater detail. One promising technique is the use of very long baseline interferometry, VLBI, which involves connecting a network of radio telescopes around the world to create a virtual telescope as large as the Earth itself. This technique allows scientists to observe black holes and their jets with unprecedented resolution, revealing finer details about the structure and behavior of these enigmatic objects. In addition to VLBI, the advent of the Event Horizon Telescope, EHT, has provided another breakthrough in our understanding of black holes. In 2019, the EHT team released the first-ever image of a black hole's event horizon, the shadow, cast by a supermassive black hole in the center of the galaxy M87. This achievement has provided invaluable insight into the nature of black holes and the behavior of matter in their immediate vicinity. The next step for the EHT and other observational platforms is to continue studying black holes and their jets, with the goal of uncovering more information about how these jets are launched and how they impact their surrounding galaxies. On a theoretical front, astrophysicists are working to refine models of jet formation, often turning to complex simulations to replicate the conditions around black holes. These simulations use supercomputers to model the behavior of matter, magnetic fields, and radiation under extreme conditions. By adjusting variables and comparing simulated results with real-world observations, scientists can test their theories and build a more comprehensive picture of how black hole jets behave. These simulations have been instrumental in understanding the dynamics of jet formation, the interactions between magnetic fields and accretion disks, and the role of the black hole's spin in jet launching. Furthermore, advancements in particle physics have opened up new avenues for understanding the high-energy particles that are accelerated by black hole jets. One of the most remarkable features of these jets is the fact that they can accelerate particles to speeds close to that of light, producing high-energy photons and cosmic rays. These energetic particles, when detected on Earth, provide valuable information about the conditions in the immediate vicinity of black holes. By studying the energy spectrum of particles emitted by black hole jets, scientists can learn about the temperature, density, and magnetic fields near the event horizon. This, in turn, allows researchers to test models of particle acceleration and probe the physics of high-energy processes in the universe. In addition to high-energy particles, black hole jets are also sources of intense electromagnetic radiation, spanning the entire spectrum from radio waves to gamma rays. This radiation is a direct consequence of the high-energy processes occurring in the jets, and it provides a wealth of information about the conditions surrounding black holes. For example, the observation of synchrotron radiation, produced when charged particles move at relativistic speeds through magnetic fields, has been used to probe the structure of black hole jets and map their orientation and composition. One area of growing interest is the study of the impact that black hole jets have on their surrounding environments. As previously mentioned, these jets have the potential to influence galaxy evolution, from regulating star formation to shaping the large-scale structure of the universe. However, the exact nature of this influence is still not fully understood. Recent research has suggested that jets may play a larger role in galactic feedback mechanisms than previously thought, with black hole outflows potentially determining the fate of galaxies by regulating the flow of gas and energy within them. In some galaxies, jets have been observed to interact with large clouds of gas, triggering shock waves and turbulence that can lead to the formation of new stars. In other galaxies, the energy from black hole jets has been shown to prevent gas from cooling and collapsing, suppressing star formation and effectively halting the growth of the galaxy. The interaction between black hole jets and their host galaxies is complex and highly dependent on a variety of factors, including the size and orientation of the jet, the amount of gas available for star formation, and the overall environment of the galaxy. Understanding these interactions is critical for understanding how galaxies evolve over time and how black holes influence the cosmic landscape. Ultimately, the study of black hole jets is not just about understanding a single phenomenon in isolation. It is about gaining insight into the broader processes that govern the universe. The behavior of black holes and their jets has implications for everything from the formation of galaxies to the acceleration of particles to relativistic speeds. By continuing to study these extraordinary objects, we may one day be able to unlock some of the deepest mysteries of the cosmos, revealing the true nature of spacetime, gravity, and the forces that shape the universe itself. As we explore the further mysteries of black hole jets, it's important to appreciate just how much these enigmatic features of the universe challenge our understanding of fundamental physics. While we have made significant strides in observing and modeling the behavior of black hole jets, there are still countless questions to be answered. How do they interact with the surrounding spacetime? What mechanisms are responsible for their incredible speeds? And how can we better observe and measure their behavior in ways that allow us to test our theories more rigorously? At the heart of these questions lies the interplay between gravity, electromagnetism, and quantum mechanics. The intense gravitational pull of a black hole affects the spacetime around it, bending light, slowing time, and warping the very fabric of reality itself. This warping of spacetime creates the conditions necessary for the formation of the accretion disk and the eventual launching of the relativistic jets. However, these jets also involve complex interactions between matter and magnetic fields, which are still not fully understood. The magnetic fields near black holes, for instance, are thought to be extremely strong, millions of times more powerful than Earth's magnetic field. This intense magnetism plays a crucial role in shaping the jets, but the exact process by which it funnels material away from the black hole and accelerates it to near-light speeds remains a mystery. One promising avenue for addressing these questions is through the study of black hole spin. It is well established that black holes rotate, and this rotation has a profound impact on their surrounding environment. The spin of a black hole influences the behavior of the accretion disk, which in turn affects the characteristics of the jet. Fast-rotating black holes, for example, are thought to be much more efficient at launching powerful jets than slower-rotating ones. This is because the rotation of the black hole can twist the surrounding magnetic fields, creating structures that help channel and accelerate the material in the jet. As a result, understanding the spin of black holes and how it relates to jet formation is a critical step in understanding the underlying mechanisms at play. Another intriguing aspect of black hole jets is their potential connection to the mysterious phenomenon known as the black hole firewall. According to some theories, the region near the event horizon of a black hole may behave differently from what we currently understand. The firewall hypothesis posits that the event horizon is not a smooth boundary but is instead a place where quantum mechanical effects create extreme conditions, effectively destroying any information that crosses it. While this hypothesis remains highly controversial, some researchers speculate that black hole jets might somehow be related to these quantum effects. For example, the intense radiation and particles emitted by jets could provide clues about the behavior of spacetime and matter at the quantum level. Exploring the connections between black holes, quantum mechanics, and their jets could open entirely new avenues of research, potentially bridging the gap between general relativity and quantum theory. Moreover, the relationship between black hole jets and their host galaxies is another area of active research that has implications for both astrophysics and cosmology. As previously mentioned, black hole jets can have significant effects on the environments in which they are found. In some galaxies, the jets can provide energy that either stimulates or suppresses star formation, leading to radically different evolutionary paths. In others, the jets can expel vast amounts of matter into intergalactic space, feeding the large-scale structure of the universe. Understanding the role of black hole jets in galactic evolution is crucial for understanding how galaxies form, grow, and interact over cosmic time scales. Interestingly, the discovery of extremely powerful jets, sometimes referred to as hyperjets, has sparked a new wave of excitement in the scientific community. Hyperjets are exceptionally energetic, producing extremely high luminosities and reaching incredible distances, often stretching over millions of light years. These jets challenge our understanding of how black holes can expel such vast amounts of energy and mass, and their study could provide critical insights into the processes governing jet formation and the overall structure of the universe. Researchers are currently investigating whether these hyperjets represent a new class of phenomena or whether they are simply extreme examples of more common jet types, such as those found in active galactic nuclei, AGN. On a more practical level, the study of black hole jets has far-reaching implications for future space exploration. Understanding the dynamics of these jets could help guide the design of future space missions, particularly those involving high-energy astrophysics. For instance, studying the radiation emitted by black hole jets could inform the development of more advanced telescopes, capable of detecting faint signals from distant jets and offering a clearer picture of the extreme environments surrounding black holes. Moreover, investigating the role of black hole jets in cosmic ray acceleration could provide critical insights into the processes behind high-energy particles that constantly bombard Earth. By learning more about these high-energy phenomena, scientists may be able to better predict and even mitigate the effects of cosmic radiation on future space missions, ensuring the safety of astronauts and spacecraft. In the future, one of the most exciting prospects in black hole research is the continued development of multimessenger astronomy. This emerging field combines observations across different types of electromagnetic radiation, such as radio, X-ray, and gamma-ray, with gravitational wave data, neutrino detections, and cosmic ray measurements. By combining these various forms of data, scientists can paint a more complete picture of the environment around black holes and their jets. This multi-messenger approach is already yielding fascinating results, such as the detection of gravitational waves from black hole mergers, and it holds great promise for unlocking even more of the mysteries surrounding black hole jets. A key aspect of this research is the increasing role of artificial intelligence, AI, and machine learning in analyzing the vast amounts of data generated by observatories and simulations. With the ability to process enormous datasets far more quickly and accurately than human researchers alone, AI is poised to revolutionize the way we study black holes and their jets. For example, AI algorithms can be trained to identify subtle patterns in light curves, spectral data, and spatial distributions that might be overlooked by traditional methods. These techniques have already been used to identify new classes of astrophysical objects and phenomena, and they are likely to play a major role in the study of black hole jets in the coming years. While much remains unknown about the true nature of black hole jets, we have made remarkable progress in our understanding of these cosmic wonders. As our technology improves, so too does our ability to observe and model the behavior of black holes in ever greater detail. Whether through the development of new telescopes, more advanced simulations, or the application of machine learning techniques, we are on the cusp of a new era in black hole research. In the years to come, scientists will continue to refine their models, gather new data, and propose innovative theories about the formation, acceleration, and impact of black hole jets. With every discovery, we inch closer to understanding not just the behavior of black holes, but the fundamental nature of the universe itself. These cosmic particle accelerators, with their enigmatic jets of high-energy particles, continue to be a rich source of inspiration for both scientists and the public alike. Their study is not only a journey into the depths of space but also a journey into the heart of some of the most profound questions about the nature of reality. As we continue to probe the secrets of black hole jets, we are bound to uncover even more mind-bending truths about the universe and the forces that shape it. As we continue our journey into the realm of black hole jets, one of the most intriguing questions is how these cosmic particle accelerators could be linked to the very fabric of the universe. While much of the research so far has focused on understanding the mechanics of the jets themselves, their formation, acceleration, and energy output, there is a growing interest in how these jets might be connected to larger-scale phenomena, like galaxy formation and the evolution of the universe. One fascinating aspect of black hole jets is their potential role in the feedback mechanisms that influence the evolution of galaxies. In some cases, the energy and matter released by black hole jets can prevent new stars from forming in their host galaxies, essentially shutting off the star formation process. This feedback is thought to play a critical role in regulating the growth of galaxies and ensuring that they don't grow too large or too rapidly. The precise mechanisms behind this feedback, and how they vary depending on the size and type of black hole involved, remain areas of active research. In particular, supermassive black holes, those with masses millions to billions of times greater than the Sun, are thought to be central to the regulation of their host galaxies. As these black holes grow, they can accumulate vast amounts of matter in the form of gas and dust, forming accretion disks and eventually launching powerful jets. The energy released by these jets can heat the surrounding gas, preventing it from cooling and condensing into new stars. This phenomenon, known as AGN feedback, is a key factor in the evolution of large galaxies, and it suggests that black holes and galaxies are intimately connected, with one influencing the growth and behavior of the other in a delicate balance. However, black hole jets don't just suppress star formation, they can also stimulate it in certain cases. The high-energy radiation and shocks produced by jets can compress gas clouds, triggering the formation of new stars. This process has been observed in some galaxies, where the jets from active supermassive black holes appear to play a role in the birth of new stars. Understanding the conditions under which jets promote star formation, as opposed to suppressing it, could offer valuable insights into the complex interplay between black holes, galaxies, and the broader universe. Moreover, black hole jets are not only important on the galactic scale but can also have far-reaching effects on the intergalactic medium, the vast expanse of gas and dust that fills the space between galaxies. When jets are powerful enough, they can extend over millions of light years, injecting energy into the intergalactic medium and influencing the overall structure of the universe. This process is known as cosmic feedback, and it plays a critical role in shaping the large-scale structure of the cosmos. One of the key areas of focus in this research is the way that black hole jets contribute to the formation of large-scale cosmic structures, such as galaxy clusters. Galaxy clusters are vast collections of galaxies bound together by gravity, and they are some of the largest structures in the universe. Black holes, particularly the supermassive ones at the centers of these clusters, can have a profound impact on the gas and plasma that fill these regions. The jets produced by these black holes can heat the gas in the cluster, preventing it from cooling and condensing into new stars. This feedback process is thought to be essential for maintaining the stability of galaxy clusters and preventing them from collapsing under their own gravity. The connection between black hole jets and the large-scale structure of the universe also raises questions about the origin and evolution of cosmic magnetic fields. The immense magnetic fields generated by black holes and their jets are thought to be a key factor in shaping the behavior of the surrounding environment. These magnetic fields can extend over vast distances, influencing the motion of charged particles and the formation of structures like filaments and voids. Understanding how black hole jets contribute to the generation and evolution of cosmic magnetic fields is an exciting frontier in astrophysical research. One of the most exciting aspects of studying black hole jets is the potential for discovering entirely new phenomena. While we have made great strides in understanding the mechanics of jet formation and their impact on their surroundings, there are still many unanswered questions. For example, some researchers have proposed that black hole jets could be responsible for the mysterious cosmic rays that bombard Earth from distant sources. Cosmic rays are high-energy particles that travel across vast distances from unknown origins, and understanding how black hole jets might be involved in their creation could lead to groundbreaking discoveries in particle physics and cosmology. Another fascinating possibility is that black hole jets could be connected to the concept of dark matter, an invisible and mysterious substance that makes up most of the universe's mass. While dark matter has yet to be directly detected, it is thought to interact with ordinary matter through gravity, and its presence is inferred from its gravitational effects on visible matter. Some researchers speculate that black hole jets might play a role in the distribution and behavior of dark matter, potentially offering clues about this elusive substance. Investigating the relationship between black hole jets and dark matter could open up new avenues of research that may eventually lead to a deeper understanding of the fundamental nature of the universe. As our technology and observational techniques continue to improve, we are likely to uncover even more mysteries surrounding black hole jets. In the near future, advanced space telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope will provide unprecedented views of black holes and their jets, allowing scientists to probe these enigmatic phenomena with greater detail than ever before. These instruments will be able to observe black hole jets across a range of wavelengths, from radio waves to X-rays, providing a wealth of data that will help refine our models and deepen our understanding of these cosmic particle accelerators. In addition to space-based telescopes, ground-based observatories are also making significant contributions to black hole research. The Event Horizon Telescope, for instance, has already provided the first-ever image of a black hole's event horizon, revealing a bright ring of light surrounding the shadow of the black hole. Future observations with the Event Horizon Telescope and similar facilities will continue to shed light on the mysterious behavior of black holes and their jets, offering new insights into the complex physics that govern these extreme objects. Ultimately, the study of black hole jets is not just about understanding these cosmic phenomena in isolation. It's about understanding how the universe works on the grandest scales. Black holes and their jets are intimately connected to the formation of galaxies, the evolution of the cosmos, and the very structure of spacetime itself. By studying these enigmatic features of the universe, we are not just learning more about black holes, we are learning more about the fundamental forces that govern all of reality. As our knowledge of black hole jets continues to grow, so too does our understanding of the universe. With each new discovery, we move closer to answering some of the most profound questions in science. How do black holes influence the evolution of galaxies? What are the mechanisms behind the formation and acceleration of jets? How do black hole jets impact the fabric of spacetime itself? These questions may one day lead to a unified theory of the universe, bridging the gap between general relativity and quantum mechanics and offering a deeper understanding of the forces that shape everything we see and experience. For now, black hole jets remain one of the most captivating mysteries in astrophysics, inspiring both awe and curiosity. As we continue to study these cosmic particle accelerators, we are sure to unlock new insights into the nature of black holes, the universe, and the fundamental forces that govern the cosmos. The journey to unravel the mysteries of black hole jets is far from over, and it promises to be one of the most exciting and rewarding scientific quests of our time. As the exploration of black hole jets continues to unfold, it's becoming increasingly clear that these phenomena are much more than just cosmic curiosities. They hold the key to some of the most fundamental questions about the universe, particularly when it comes to understanding the larger structures that make up the cosmos. From galaxy formation to the distribution of cosmic matter, black hole jets are far from being simple side effects of a black hole's existence. They are active players in shaping the universe itself. One of the more profound areas of study related to black hole jets is their ability to influence the intergalactic medium. The intergalactic medium refers to the vast stretches of space between galaxies, which contain low-density gas and plasma. It is here, in this almost empty space, that the effect of black hole jets becomes incredibly important. The energy released by these jets can help regulate the density of the intergalactic medium, maintaining a delicate balance that influences the entire evolution of galactic structures. To imagine this, picture a scenario where a supermassive black hole in the center of a galaxy begins emitting a powerful jet of particles. These particles, traveling at nearly the speed of light, can stretch out over vast distances, impacting not just the black hole's host galaxy, but also the surrounding galaxies and the space in between. The energy carried by these jets can heat the gas in the intergalactic medium, preventing it from collapsing under gravity and forming new stars too quickly. This is one of the key ways black hole jets help regulate the pace of galaxy growth, ensuring that the universe does not spiral into chaos with too many stars forming too fast. But this is only part of the story. There's also evidence to suggest that black hole jets might play a crucial role in the reionization of the universe, a process that occurred shortly after the Big Bang. During the first few 100 million years of the universe's existence, the cosmos was a hot, dense soup of particles, and the universe was opaque to light. As the universe expanded and cooled, the first atoms began to form, and the universe became transparent. This process, known as the reionization epoch, was driven by the first stars and galaxies, which emitted radiation that ionized the hydrogen gas surrounding them. But black holes, particularly the ones found at the centers of the earliest galaxies, may have had a hand in this process, contributing to the universe's transition from opaque to transparent. While this idea is still being studied, it's possible that the high-energy radiation and shockwaves generated by black hole jets could have played a role in reionizing the universe, helping to break apart the hydrogen atoms that were prevalent in the early universe. The energy from these jets would have provided an additional source of heat and radiation that could have contributed to the reionization, helping to speed up this crucial phase in cosmic history. The study of black hole jets also intersects with the cutting-edge field of high-energy particle physics. These jets, which are composed of charged particles such as electrons, protons, and ions, are accelerated to relativistic speeds that are close to the speed of light, by the intense magnetic field surrounding a black hole. The physics of how this acceleration takes place is still not fully understood, but scientists believe that magnetic reconnection, where magnetic fields reconnect and release energy, plays a significant role in this process. Magnetic reconnection is a process that occurs when magnetic fields change their configuration, releasing vast amounts of energy in the form of radiation and energetic particles. This is believed to be a crucial part of the mechanism that accelerates particles in black hole jets to relativistic speeds. The exact details of how magnetic reconnection works in the extreme environment of a black hole are still being explored, but this process could potentially provide insights into the fundamental workings of high-energy particle acceleration across the universe. In fact, studying the particles in black hole jets is one of the ways astrophysicists are beginning to understand more about the nature of the universe's most energetic particles, cosmic rays. Cosmic rays are high-energy particles that travel through space and occasionally reach Earth, where they interact with our atmosphere to produce secondary particles that scientists can detect. However, the origins of these cosmic rays remain one of the great mysteries in physics. By studying the jets from black holes, particularly in active galactic nuclei, Researchers may be able to uncover clues about where these cosmic rays originate and how they acquire their extreme energies. This connection between black hole jets and cosmic rays raises another intriguing possibility: the role of black holes in the broader context of high-energy astrophysics. Black holes, particularly the supermassive ones found at the centers of active galaxies, are thought to be some of the most powerful particle accelerators in the universe. As their jets spew out particles at near-light speeds, these jets could be responsible for producing the most energetic particles in the universe, including ultra-high-energy cosmic rays. These rays, which have energies far exceeding those produced by any human-made particle accelerator, challenge our understanding of physics, and studying black hole jets may offer key insights into how these extreme energies are generated. Moreover, the high-energy environments around black holes could provide a natural laboratory for studying particle physics in conditions that are impossible to replicate on Earth. For example, the gravitational forces near a black hole are so strong that they warp spacetime itself, creating conditions that allow particles to behave in ways that we cannot observe in laboratory experiments. This makes black holes a natural testing ground for theories in physics that involve extreme gravitational fields, such as quantum gravity and string theory. But it's not just the physics of black holes and their jets that make them so fascinating. The study of black hole jets also raises questions about the nature of spacetime itself. The relativistic speeds at which particles travel in black hole jets can provide a direct test of Einstein's theory of general relativity, particularly in regions where gravity is extremely strong. General relativity predicts that spacetime should curve around massive objects like black holes, and by observing the behavior of particles in jets, scientists can test this prediction under the most extreme conditions. Furthermore, the way in which these jets interact with the surrounding gas and matter has implications for our understanding of the structure of spacetime on a cosmic scale. The energy released by the jets can distort the gas clouds and influence the behavior of the galaxy itself. As a result, black hole jets may provide clues not only about the forces that shape galaxies, but also about the fundamental nature of the universe's underlying fabric. In recent years, the study of black hole jets has also advanced thanks to technological innovations in observational astronomy. With the advent of radio telescopes like the Event Horizon Telescope, scientists have been able to directly observe the behavior of black holes and their jets in more detail than ever before. The groundbreaking image of the supermassive black hole in the center of the galaxy M87, captured by the Event Horizon Telescope, marked a major milestone in our ability to study black holes and their surroundings. This image, while blurry due to the vast distances involved, revealed the shadow of the black hole and provided direct evidence of the existence of its jet. As these technological advancements continue, the resolution of our observations will only improve, allowing us to probe black hole jets with greater precision. This will likely lead to new discoveries that challenge our current understanding of astrophysics, providing valuable insights into everything from the formation of galaxies to the behavior of matter under extreme gravitational conditions. The future of black hole jet research is not just about improving existing technology, it's also about pushing the boundaries of our theoretical models. As we continue to observe black holes and their jets, scientists will need to refine our models of how these jets form, how they are accelerated, and how they interact with their surroundings. This may involve the development of new theories that combine the principles of general relativity with quantum mechanics, as black holes are objects where both of these theories are crucial to understanding their behavior. The investigation into black hole jets promises to be one of the most exciting and productive areas of research in astrophysics. These jets are more than just fascinating cosmic phenomena, they are central to some of the most profound questions in science. By continuing to explore these cosmic particle accelerators, we are not just learning about black holes, we are learning about the very nature of the universe itself, and how it works on both the grandest and most fundamental scales. As we continue to explore the mysteries of black hole jets, it's important to remember that these phenomena don't exist in isolation. They are intimately connected to the larger structure of the universe, from galaxies to the intergalactic medium. The study of black hole jets doesn't just shed light on the behavior of black holes themselves but also on the way energy flows through the cosmos, influencing galaxies, clusters, and even the vast voids between them. These jets are cosmic engines, powering and shaping the universe in ways we're only beginning to understand. One crucial aspect of black hole jets that researchers are particularly interested in is the role they play in the life cycle of galaxies. We know that supermassive black holes exist at the center of nearly all large galaxies, and their activity, whether dormant or active, has a significant effect on the galaxy's evolution. In fact, the process of galaxy formation and growth is deeply linked to the activity of these black holes. Black hole jets, through their energy output and interactions with the surrounding gas and dust, can either promote or hinder the formation of new stars, playing a central role in how a galaxy matures. In a process known as feedback, the energy emitted by the jets can influence the surrounding gas in ways that either promote star formation or suppress it. When black hole jets heat up the surrounding gas, it can prevent it from cooling down and condensing to form new stars. In this way, black hole jets can act as a regulator, preventing galaxies from growing too quickly. This process is thought to be responsible for what is known as galaxy quenching, or the rate of star formation in a galaxy slows down or stops altogether. However, in certain cases, black hole jets can have the opposite effect, injecting energy into the surrounding gas in a way that stimulates star formation. This is particularly evident in galaxies that are actively undergoing mergers, where the interaction of the black hole jets with the gas can trigger bursts of star formation. These complex dynamics show how black hole jets are integral to the process of galaxy evolution, acting as both an agent of destruction and creation, depending on the circumstances. Another fascinating aspect of black hole jets is their connection to the larger-scale structure of the universe. While the jets themselves are focused around individual black holes, their impact extends far beyond these localized regions. Black hole jets can influence the environment around them on scales that reach far into intergalactic space. For example, the jets from a supermassive black hole in a galaxy can send shockwaves through the surrounding gas, creating large-scale structures like galaxy clusters. These clusters are vast collections of galaxies, bound together by gravity, and the gas within them can be heated and influenced by the energy from black hole jets. In some cases, black hole jets are thought to help regulate the cooling of gas in galaxy clusters. Without this process, the gas in these clusters could cool too rapidly, triggering an overabundance of star formation and leading to a chaotic environment. Instead, the energy from the black hole jets heats up the gas, preventing it from cooling too quickly and ensuring that the cluster remains in a more stable state. This feedback mechanism is critical to understanding the balance of matter and energy in these massive structures. The importance of black hole jets in the cosmic landscape also extends to their role in the so-called cosmic web, a vast, interconnected network of galaxies, dark matter, and gas that spans the entire universe. The cosmic web is the large-scale structure of the universe, and it is shaped by the gravitational pull of galaxies and the gas that surrounds them. Black hole jets, with their enormous energy output, can influence this web by affecting the distribution of gas and matter across vast distances. Through their interactions with the intergalactic medium, black hole jets can help to shape the way galaxies are connected and the way matter flows through the universe. In addition to their impact on galaxies and the cosmic web, black hole jets also play a central role in the ongoing search for new frontiers in astrophysics. As we continue to refine our observations and deepen our understanding of the physics behind black hole jets, we are also uncovering new aspects of the universe's most extreme environments. The study of these jets pushes the boundaries of our knowledge about the fundamental forces of nature, including gravity, electromagnetism, and particle physics. For instance, as we observe the high-energy particles that are accelerated in black hole jets, we are learning more about the nature of cosmic rays. These particles, which travel through space at nearly the speed of light, are among the most energetic objects in the universe, and their origins have long been a mystery. It is believed that black hole jets play a significant role in the creation and acceleration of these cosmic rays. By studying the jets, scientists hope to uncover new insights into how these particles are generated and how they interact with their surroundings. Moreover, the study of black hole jets is helping to refine our understanding of the nature of gravity itself. The extreme gravitational fields around black holes offer a natural laboratory for testing Einstein's theory of general relativity. By observing how light and particles behave near these massive objects, scientists can test the limits of our current theories and gain new insights into the fundamental nature of spacetime. This is particularly important when it comes to understanding the behavior of matter and energy in the vicinity of a black hole, where gravity is so intense that it warps space and time in ways that are impossible to replicate on Earth. As we push forward with research into black hole jets, it's clear that these phenomena will continue to offer valuable clues about the workings of the universe. From galaxy formation and evolution to the study of high-energy particles and the behavior of spacetime, black hole jets are at the center of many of the most exciting and profound questions in astrophysics. With the continued advancement of observational technology and theoretical models, we are only beginning to scratch the surface of what these cosmic particle accelerators can teach us. The future of black hole jet research is undoubtedly bright, with new discoveries on the horizon that could reshape our understanding of the universe. As we continue to probe these mysterious jets with ever more advanced telescopes and experiments, we may uncover new phenomena that challenge our existing knowledge and open up entirely new areas of inquiry. The more we learn about these enigmatic jets, the more we realize that they are not just fascinating cosmic oddities. They are central to the way the universe operates, and they hold the key to understanding the deepest secrets of the cosmos. In the grand scheme of things, the study of black hole jets may one day help to answer some of the most fundamental questions that humanity has asked since the dawn of time. What is the nature of space and time? How did the universe evolve into the complex and beautiful structure that we see today? What forces are at work on the grandest scales, shaping the galaxies, stars, and planets that make up the universe? Black hole jets are an integral part of these questions, and as our understanding of them deepens, so too will our understanding of the very fabric of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.